So should I start? So the my presentation is quite unusual for this conference because it contains only classical mechanics. But maybe one excuse for such topic is because here is Newton Institute and using of Newton laws is not completely forbidden. So this is just a slide to say that I am not in this area. It should be a pointer some here. Oh. To push where? To have a pointer. Push this one. About say 7-10 years ago, we introduced term vibrodynamics with late Professor Udovich, as area in mechanics, mainly operating with averaging methods. And this is not important for this audience. Actually, in terms of ODEs, PDEs, it represents theory of equations with oscillating coefficients. And in this presentation, I wish to give very brief description of, first of all, some method which connects the area of, say, micro robots with classical mechanics, and consider some simple locomotion devices. So, first of all, classical pendulum. Simple picture, pivot, bob, rod of constant length, L. The point is, this is pivot is oscillating vertically, periodically, and this is so-called Kapitsa pendulum or Stephenson Kapitsa pendulum, and also known as inverted pendulum. Here I use it just to demonstrate the method, which is partially known to everyone, but partially should be kind of explained. This is the classical equation for pendulum, which also everyone knows. Phi is the angle, G is a gravity, which is minus G y component, and this is vertical acceleration, which appears as modulated gravity, of course, according to Einstein's principle of equivalence. Sine phi is usually. So vertical oscillations are given function of omega t with some frequency, periodic function, of course. We have basic frequency for pendulum, and we have a small parameter which says that frequency of oscillation of pendulum is much higher than self-oscillations. So dimensionless equation appeared here, once again there, and of course very well common knowledge is to use multi-scale, or in this case two-timing method. Actually, this equation explicitly contains two-time scale, slow time scale, which is t, which is affiliated to omega naught, to self-oscillations, and another time scale, omega t, where here omega already dimensionless, as well as t, which is enforced vibrations of the pivot. And how to solve it? In order to solve it, we should introduce something for vertical oscillations, which is presented here. So if oscillating function like sine is order 1, it should be 1 over omega. Why? This is probably everyone knows. This is because we consider class of functions which some average and small oscillations around it. And we in this class of functions, we consider for simplicity 2 pi periodic in fast time only functions. We operate with this heuristic step. Mathematically, it's of course should be justified that instead of one time variable, we introduce two independent time variable after, of course, using the chain rule, and we use the average over the fast time only. So this is quite well known. So we have, instead of ODE, we are solving PDE, of course, now with two time variables, and we do successive approximation as everyone does, which is quite a routine procedure. And remarkably, that fast equation appears separately in the main approximations. So, and just procedure of considering average and oscillating equation gives you well-known equations for slow oscillation of pendulum, which is this classical result of upside down pendulum from energy point of view. So zero is classical equilibria, and here is inverted equilibria with this potential energy. So where things inside which are not well known, there, of course, the justification of this, people have different views. Simplest possible is, of course, just direct substitution of final solution after replacing variable backs to original t. And another question, why the amplitude of pivot is taken in a such strange form. It should, if omega goes to infinity, then it should decrease as omega. And actually the answer is that this is the only possibility. If you take any other possibility, your asymptotic solution will fail. And this is so-called distinguished limit principle or distinguished limit theorem, which can be easily explained on this kind of abstract equations of ODE. Now it's just abstract ODE with going for the same procedure, but here instead of vertical oscillation of pendulum, you will have another small parameter. So omega is large parameter, and here is another parameter which appears as displacement in vertical direction. Second small parameter, but of course for rigorous procedure you should establish connection between those two parameters with unknown alpha, and so on. Procedure will produce the values of these parameters, alpha and beta, in this procedure. And this is kind of uniqueness of asymptotic procedure. So this is not very well known, and different people, more importantly, there are many different viewpoints on this. One viewpoint, it's distinguished limit theorems. If questions, then I can discuss it. Now, micro-robot. Of course, you know that this is interesting directions. There are several constructions to invent small constructions which are able for locomotion. And in my case, I use, of course, Navier-Stokes equations, and after that, Stokes equation, which is known for everyone, and just no slip boundary conditions, and go along this very simple way of use Stokes solutions. Stokes solutions, 1851, probably, for a sphere, rigid sphere. So there are three examples I briefly consider. One is n-sphere robot. So this is generalization of the machine which was proposed by Ramin Golestanian some time ago, and calculations are based on the just system of equation which just says that force exerted on each sphere must be 0 in the Stokes approximation. And this could be presented in the some tensorial form with two small parameters. One small parameter is so oscillations of the rod, considered small, and another is geometrical. Radius of each sphere is small. So, and of course it should be a connection between them somehow, but procedure is absolutely the same as with the pendulum. The only exception is that slow time scale is here unknown. This is like a pendulum in weightlessness in the satellite. So it's no self-frequency, of course, for pendulum and satellite, but the same distinguished limit theorem, of course, uniquely determines the slow time scale. As well, the same is true in this situation, which I just skip because it's rather trivial exercise. Just I go to result. Result surprisingly can be presented for very general case. It can be expected from linearity. When you have n spheres, then by linearity it should be sum of all triplets on self-locomotion, on locomotion velocity, and it is. And this is sum of all g's when I introduce g's after Galistanian function officially. So, and I confess that I was not bribed for this. Yeah, yeah, because of all triplets are working, but number of triplets, say for 10 spheres will be 120, for example. It's quite impressive. But what is important that with increasing of lengths, so both self-propulsional velocity and efficiency, light hill efficiency rapidly increase. So this is a good way, in a way, to think about the increasing of parameters. So now second example, little bit more complicated. We have three spheres with three rods connected, KLM, and these three rods periodically changes with time. And question is to describe in Stokesian fluid, to describe the behavior of such system. So what is presented is immediately the answer. The method is absolutely the same. Two-timing method, distinguished limit theorem. So it is translation, proportional delta epsilon square. Again, delta, this is geometrical parameter, radius of sphere to the distance to the sphere. And epsilon is relative extension of each rod. So it's delta epsilon square order locomotion and self-rotation, which remarkably does not contain delta. It means that for rotation, you don't need to take into account interaction between the spheres. So rotation is much faster than translation. So Galistanian told me that this is kind of unknown result, surprisingly. And all coefficients are just correlations. And say this D is just some correlations between relative extensions of each rod. Tilde means exactly oscillating part of the lengths. Each LMK are scalars, just lengths. And there are many examples, for example, pure rotation or pure translations, but generically it's called epicycloid, so circle over the circle for generic trajectory. So this is purely translational motion from this side. And one more example, which I am consider as not toy. Previous I like toys, but this actually I am looking for collaborations with experimentalists. How to make a simplest machine which moves due to pure hydrodynamics. And the simplest one, as I believe, is just dumbbell connected by elastic element like spring. And if you put it to the water or whatever, glycerol, put it to vibrating table, then it will be average self-propulsion in perpendicular direction. There is average ODEs, which can be derived, which is also the same absolutely procedure, but with, of course, with internal specific. There is expressions for, of course, generically, this kind of dumbbell also rotates and propagates. And also generically, it also epicycloids. But for some classes of parameters, which are written here, there are straight lines. Namely, if parameter phi capital is between minus and plus 1, this is what is AB is oscillations of the table in two directions, and K is elasticity somehow. So if parameters are in certain range, then it propagates just straightforwardly, and this could be an interesting option for construction of micro-robot based on acoustics, on purely oscillating fields, you know, and which shows that in oscillating fields, usually very simple construction, they have locomotion. Those some papers are based. I have 2 more minutes or 2 more, yeah, 5 more. Okay, couple of papers about sphere and this dumbbell are published, but the same method I have applied for many systems, including, by the way, 2007, it is vibrational Friedrichs transition in liquid crystals. And what this paper is about, it's actually inverted Kapitsa pendulum for pneumatics. It was initiated by some paper of, known paper of Piotr Kapitsa. So I considered here just pneumatics, and the main result of this paper in a layer between 2 walls. And you know Friedrichs transition when you have perpendicular magnetic field, and after some critical magnetic field you have a kind of instability called Friedrichs transition of overturning of director field. And in this paper it is shown that vibration can do the same, high frequency vibrations, and it's moreover there is mathematical equivalence. You can just take theory of Friedrichs transition by magnetic field, change the letters magnetic field to average vibrations, and it will be the same theory. So this one. And why I use opportunity to quote this paper, which is rather old, since first of all this is a program on liquid crystals, and second, I'm looking for years for experimentalists to do this, and if occasionally anyone can advise something, actually 2 experiments, one on Friedrichs transition and another on dumbbell micro-robot, and second one I have some interest from some people, but first one, this one, still open problem. So that's all my talk essentially. You see, it's about 2 timing.
Your proposed micro-robot with 2 spheres and a spring, you would, as it were, drive it by having acoustic vibrations of the fluid around them on a longer length scale. In many high-frequency acoustic experiments, you would also get in the fluid itself, depending on the geometry, you would get steady streaming
called acoustic streaming.
Acoustic streaming.
Yeah, true.
And I would like to know if you've considered the combination of those, if they conflict, how the two mechanisms interact.
They do not interact, they're independent essentially. So you have, of course, secondary flows and you have superimposed locomotion of micro-robots, which should be considered for each particular case separately. But of course, in some cases, acoustic streaming is very much suppressed. For example, if you consider, because it's no much use of put micro-robots to the ocean, probably, yeah? Huge massive of water. But if you put it in, say, porous media where capillaries of order microns also, then acoustic streaming will be seriously suppressed, of course.
But some people use acoustic streaming in very small spaces to maneuver biological cells and cause them to rupture. And all
But you
sorts of
see,
things. So, I mean, they're
yeah. Agree. But there are two. You see, when you have two options to move something, it's better than one option. that's actually the answer. If you are smart and you know that there are various possibilities to move, and one works better, one works worse, and you should adapt to the situation. Which one is which to choose?
Okay, so let's then.